Okay, so we'll just, to get it on the recording here, so we have the ball that's accelerating when it reaches the top, but that's not because it's changing speed, it's because of turning. Because the ball speed stays constant. Okay, so here we go. So we're talking about multivariable, real-valued multivariable functions. What does that mean? Multivariable, real-valued functions. Means what? Yeah, Richard.
That there's two inputs, more than one independent variable.
Okay.
And real value means that it's not like a vector function.
Okay. It's not like a vector function, so what does that when you talk about the real value, what does that refer to? Right. It's just the dependent variable is just a number. And so we've seen two ways that we represent those visually or graphically. What are the two ways that we can represent real valued functions of two variables? Real valued functions of two variables. You've seen that now in your web work. There are two ways to represent those graphically. What's one of them? Yeah, Rebecca. Yeah, a contour map. So that's actually a two-dimensional rendering of a multivariable function, right? So you're in your two dimensions, or your plane is basically a point in the plane is your combination of your two independent variables, and then what your contour line you're on tells you what the output, the z, corresponding z, would be at that value. Okay, and then the other way is? Andrew? Yeah, just the graph in R3, right? So it's surface, right? So we know equations of x, y, and z, which is like what these functions are, give graphs or surfaces in R3. So pick an x, y, gives you, that's like the input, and then the value of z on the surface is the output. Okay, so we're going to talk about rate of change because this is calculus. So let's review. So rate of change for these multivariable functions. So let's review just rate of change in general. We've got to have a good concept of rate of change. So if you're traveling on a highway and your phone is telling you that you're moving 90 feet per second, what is that? That's the rate of change of distance in feet with respect to time elapsed. What does that mean, that you're moving 90 feet per second? What does that mean, that you're moving 90 feet per second? Harris? So every second, you go 90 more feet. Is that right? Everyone who's not had me before is nodding, and those who have not had me before know that there's a different answer, or a better answer. What's the better answer than this? The more broad answer. This is a very narrow meaning of 90 feet per second. So when we talk about rate of change in calculus, we want a broader meaning for that. So, Alex, what do you say?
Any given change in the number of seconds is equal to 90 times the change in the number of feet. Sorry, other graph.
All right, so he's onto it. So how far would you go in 2 seconds? And how far would you go in a half second?
45.
And in a third of a second?
30.
So does 90 feet per second only tell you that you go 90 feet in 1 second? Does it tell you more than that? Yeah, it tells you a lot more than that, right? It tells you how far you go in a tenth of a second, which is 9 feet. So what it tells you how far you go in any change in time. In any change in time, it tells you how far you go. And how far do you go in any change of time? 90 times that change in time. So this is our good, broad meaning. For any change in time, it would be like dx, right? For any change in time, the change in distance, like dy, is 90 times that change in time. So yes, it does tell you that you go 90 feet in a second, but it tells you a lot more than that, right? It tells you how far you go in any change in time, as long as you stay at that constant rate. So when we're working with these multivariable and vector functions, and we're talking about rate of change. We want to have this same thinking about those rates of change. All right, yeah, so for any small change, so then if you have a changing rate, we can still use this and just qualify that we need a very small change in the independent variable. As long as you have a small enough change in the independent variable, this still holds. Why? Because curves, if you zoom in far enough, become what? Straight lines, right? If you zoom in far enough on a curve, you've got a straight line. And so you have, like, for that little interval, you have a constant rate of change. So you can still apply this principle. So whether it's constant or changing rate, as long as we say, for a small change in independent variable, the change in the dependent variable is the rate times the change in independent. Okay. So two variable real valued functions have the form, we know z equals f of x, y. Conventionally, we use x and y for independent variables. So then when we think of rate of change, what's different now? We think about rate of change. What's that? So what's our dependent variable? So rate of change is always about the dependent variable with respect to a change in independent. So what's going to happen now? What's that? So you're going to have two rates of change, right? You're going to have two rates of change. You're going to have, we're going to look at the rate of change of what? Z with respect to x or y, right? So there's going to be two rates of change, z with respect to x and z with respect to y. So we call these partial derivatives, okay? So what would happen here? We'd have, given a change in x, the change in z would be that rate with respect to x times the change in x, and similarly with y. So the same principle holds that we just talked about, but you're just going to let one of your independent variables change a little bit, and that will define, all right, then you'll get a corresponding change in z according to just that variable. So these are called the partial derivatives. Partial derivative with respect to x, partial derivative with respect to y. But the meaning is the same. So if we're talking about the partial derivative with respect to x, then what do we have to say about y then, if we're focusing in on the partial derivative with respect to x? We want to know the change in z given a change in x, then what do we have to, and what's going to happen with y?
Treat y like a constant.
Yeah, so we want to hold y fixed. All right, so when we're talking about the partial derivative with respect to x, we're talking about y staying fixed, and vice versa. When you're talking about the partial derivative with respect to y, you're holding x constant. So making a small change in x to apply the partial with respect to x means keeping y constant. And the reverse of that. And the reverse of that. So then really it's the same. So if we want to look at the partial derivative with respect to x, we just hold y constant, and then now we have the same analysis that we've done before. For any change in x, the change in z is the derivative times the change in x. All right, so here's some common notations. So we have derivative notation, but instead of using d, now we use this Greek delta, lowercase Greek delta. And then you'll also see this a lot. So then there's y2. Scared. I'm recording. Okay, so yeah, so you'll also see besides the delta z, delta x, or delta z, delta y, f with a subscript x. So if the function is f, you see f with a subscript x, that's indicating the partial derivative with respect to x. F subscript y, same thing. I gotta find my pen here. Where's Emma? Yeah. Okay, so recall that we have 4 primary representations of these 2 variable real value functions that we talked about last time. And so function definition, a surface in R3, a table of values, and a contour plot. So these are all ways to represent these functions of 2 variables. So we want to look at how does rate of change, we're going to determine and analyze the partial derivatives in each of the contexts. So in each one of these contexts, what is it like thinking about partial derivatives and rate of change? So we'll start with function definition. So this is like the algebra, right? This is like the algebra aspect of all this. So if I've got h of xy is x cubed minus 4x squared plus y to the 4th, I want to find h sub x of xy. Which is the partial of h with respect to x. And so what did we say to do this? We have to think of y is a constant. So y is a constant. When constants are multiplied by functions of x, they have a certain, property in taking the derivative. When there's so like for instance, let's just do it. So we're going to find the derivative with respect to x. So derivative of x cubed is 3x squared. Okay, so now derivative of 4xy squared with respect to x means y squared is constant. When constants are multiplied by the function, what happens to those? They just come along for the ride, right? Just keep them. So the derivative will be minus 4y squared. Just like you kept the 4 to do the derivative of 4x, you keep the y squared because it's a constant. All right, and now plus y to the 4th. With respect to x, its derivative is 0. So that is a new function, right? It's a new multivariable function given any point x and y. This tells you what the rate of change with respect to x would be of our original function h. Okay, so write that down. And then so hy, same thing. Derivative will be derivative of x cubed, 0. Derivative of minus 4xy squared, negative 8xy to the 1st, plus 4y cubed. So now this is a new multivariable function that tells you, given any ordered pair xy, it'll tell you what the rate of change with respect of z with respect to y is of the function h. All right, so let's kind of practice here a little bit. So you've got those written down. So find h of x of 1, 0.5 and h sub hold on a sec. All right, before we do that, don't do that yet. So let's put that on hold, and let's talk about looking at a surface in R3. Let's look at that surface in R3. We'll use it to predict. Not that one, this one. All right, so that's the surface. And that point is the point 1, 0.5, I think. Yeah, 1, 0.5 on that surface. All right, so what does it mean to talk about the partial with respect to x? What did you guys say? When you talk about the partial with respect to x, it means z is constant, y is constant, right? So we just, if we care about what the partial with respect to x of this surface, or this function at that point, then really all we care about is what we get when y is constant. So I'm gonna turn on the plane y equals 0.5. And so all we care about is then the trace on that surface that you get when you intersect y equals 0.5. So this is keeping y constant on that surface. It follows that trace right there. Do you see that? So now x is to the left and y is coming out at us, right? See that? So before we plug in and get this partial with respect to x, what do you expect the result to be? What's that? So x is now positive x is this way, positive y is coming out at us. Yeah, Simon?
The slope with respect to z
Okay.
in that point, at that point.
Okay, and can you tell me what you expect for that then? Can you tell me anything about the value?
That one.
So 1 or negative 1?
I don't know which way.
X is coming out at us. Now x is to the left.
So positive.
Do you see that it's positive? Do you see that? So along y equals 0.5 on the surface, if you changed x a little bit, what's z going to do? Increase or decrease? Increase, right? Increase. For a little change in x, you're going to get an increase in z, meaning the partial with respect to x would be positive. Do you see it? All right? And similarly, the partial with respect to y. How do we think about that? Hold x constant. So now I'm holding x constant. And a little bit negative or a lot negative? Do you see that now? Do you see that contour right there? So this is on the surface. Was it h? On the surface for the function h. If you increase y a little bit, so this is holding x constant. If you increase y a little bit, what will happen to z? It'll go down a lot, right? Therefore, the partial derivative with respect to y, and maybe a larger negative than the x was positive, right? Okay, now find the values, and let's see if that was right. So you got your functions, and we're looking at the point x equals 1, y equals 0.5. Okay, what did you get for h sub x? Positive 2? People are getting positive 2. And what did you get for h sub y? Negative 3.5? Okay, so it agrees with what we saw, right? It agrees with what we're seeing in the graph there. That when you hold x constant and let y change, z goes down what? So how much does y have to change? Any little amount, right? Any little amount, and then z goes down how much? Negative 3.5 times that amount. So increase y any little amount. But it has to be little too, but everything's changing, right? As soon as you move away from this point 1.5, then things are different. Rates are different. So for a little change in y, a change in z will be negative 3.5 times the change in y, and for a little change in x, it was a 2. For a little change in x, the change in z, so let's show that again. The change in z is 2 times whatever your change in x is. Okay, make sense? All right. So we did that already. Okay, here's a cool, another cool illustration of this. So the displacement of millimeters of a point on a guitar string, x millimeters from the end of the string, y milliseconds after the string is plucked, is given by this function. So let's draw a picture here to explain that. Done it again here. I sure hope the video is working. Okay, so you've got this guitar string, and it's held at 2 points. So x is the distance of the string where you are along the string in millimeters. So that can vary, right? And then y is time since it was plucked, right? Time since you plucked the string. And then g of xy, or the independent variable, then is that point's displacement, either up or down, at that distance from the end and at that time, y milliseconds. Does that make sense? So at a given time, the height of the string will be different at different places. And at a given distance from the end, the height will be different based on the time, right? So both of those are varying. All right, so let's find I think these are pretty easy because they're both just as two terms isolated with x. So when we do the partial of g with respect to x, we're just going to hold on to that, right? And do the derivative of that. So let's write that out. So it's going to be what? 3 times pi over 100 cosine of this. Is that right? 3 pi over 100 cosine of that times that. Is that right? Make sense? And then this one will be exhibit A times 2.765 cosine of that. And this is just the same thing as 3 sine. Okay, so you got those written out. So we're gonna I'll give you a second to write those down. No, because it's derivative of sine, right?
Oh, yeah.
They're both derivative of sine, so they're both going to be positive cosine. We good? Questions? Okay, so 70 means what? 70 millimeters from the end of the string, and at 2.5 milliseconds. So we're going to split up so that in order to get these values. So you guys have all the three functions now. If your last name is A through G, I want you to just find the value of the function. If your last name is H through P, you're going to find the partial with respect to x at 70, 2.5. And if you're Q through Z last name, you find the partial with respect to y. And then we'll make sure you've got, this is all radians. Everything's radians. Make sure your calculator is set to radians. And as soon as you get one of them, just shout it out. We'll see if the rest of your team.
G of 70.5 is, I got 1.4285.
1.43. Someone else got that? And what's the units of that?
Millimeters.
He wants 1.43 millimeters. One more person get that in the A through G group? Yeah? Someone said yes? Sweet. Okay, so we got 3 concur on that one. All right, partial with respect to x at 72.5. Anyone get that? This is the G through P's. H through P's. Did you get something? Negative 0.326. 0.3. And just do 3, 3. Someone else get that? And all right, and then anyone, the last partial with respect to y, the Q through Z's. Don't be shy. Did you get one? No calculator, okay. Anybody got it? Don't be shy. Is that particularly harder? Come on, we got lots to do. Somebody. Wait, she did 2. 0.5?
0.5425.
Does anyone else get that? Yeah.
Yeah.
5? Okay, good.
Oh, you know what? I did it.
5.425? 23? 25. Okay. What are the units on the partial derivative with respect to x? What would the units be on that? Partial with respect to x. What is it? So it would be the z unit, which would be? But that's millimeter up and down, right? If I draw the string horizontally, right? It's up and down millimeters per left and right millimeters, right? Okay, and then what about the units on this one? He wants millimeters per millisecond. Agree with that? It's going to be amount of change up and down with the string per change in time. Okay, so now I want you guys to practice. So there's kind of lots to say now. Okay, there's more to say than just our old school rate of change with just 2 variables. So describe fully the meaning of this number, negative 0.033, and describe fully the meaning of this number, 5.425. Get a partner. Everyone's talking to somebody. Practice. What do these numbers mean? In the context of the guitar string. In the context of the guitar string. Okay, what does the 1.43 mean, first of all? What does the 1.43 mean? Kenneth, what do you think?
The 1.433 is the displacement.
Displacement? Be more specific?
Point x. Pretty much what the function definition says, displacement of these millimeters of one on a guitar string, x millimeters with the end of the string.
Where from the end of the string?
From the left. Or origin.
But 70, right? We know it's 70, right? Okay, and then also?
And then we would point on the y at 2.5.
What's the 2.5? No, the 2.5, what's the 2.5 about? Yeah, that's the time, right? So at 2.5 milliseconds after we pluck, 70 millimeters from the end of the string, what can we say? Yeah, so that point on the string is up, say up 1.43. It could be down, but it's up right now, at this moment. Okay, so that's 1.43. All right, what about the negative? So here's where we get tricky. Oh, again. Okay, so we're up 1.43, and now what does the negative 0.033 mean? Okay, Paul, go.
So the partial with respect to x is holding y constant, so that means it's at a certain point in time.
Okay.
Kind of a snapshot of the string at that time.
Okay.
So it tells us the change of this kind of slope of the string as we move across it at that certain point.
Okay, and so can we use our construct for rate of change earlier in class to talk about the meaning? We said given what? Remember?
Given a change in the independent variable.
Okay.
So in this case, it's how far you are down the string.
So given a little change, go a little bit further down the string, right? And then what would be true?
The displacement of the string would be a little bit smaller because we negative.
How much smaller would it be? We know exactly how much smaller it will be.
0.033 times the distance.
Right. All right. So go down. Let x increase a little bit. The displacement of the string will be
0.233 times.
right. So actually, the change in displacement in the string will be negative 0.33 times whatever change we have. Meaning that if we go this way, is the string going up or going down? Going down, right? At that moment in time, so the string is like this. And so given a little change in x this way, to get that how far down the string would be negative 0.033 times that change in x down the string. Remember, dz equals mx dx. Okay, what about 5.425? Somebody else? Caitlin, can you talk about what's the 5.425 mean?
For every change in milliseconds,
Okay.
the displacement in millimeters will be 5.4 millimeters or greater.
Okay, on the right track? Anyone else want to try it? So yeah, you got lots right there, but yeah, Julia.
For any small change in milliseconds from 2.5, the displacement or the holding the string distance constant, the displacement will change 5.425 times the change in blah blah. And
Just one more word. Just one more word.
is why.
No, you almost had. You just had one word to go. It was going to be perfect. So yeah. So you said at 70 millimeters, given a small change in time, the change in displacement of the string will be 5.425 times the change in time. Yeah, time. So what in time at 70 millimeters? What is the string doing right now? Now, right at this moment, at 2.5 milliseconds, at 70 millimeters, what is the string doing? Eric got it. It's moving up. It's moving up. This is positive, right? How much is it moving up? Given whatever change in time you pick, it's going up 5.425 times that change in time is how much it will go up. And it's going up because it's positive. The string is angled this way because this derivative is negative. If you move a little bit down the string, the amount that the string displacement changes is negative. Negative 0.0033 times your change in displacement. So that's why so the string is angled this way, but at that moment it's on its way up, right? So the string is angled this way, but on its way up. That's what those two derivatives, partial derivatives, tell us. Okay, so with more variables, it gets harder. There's more detail that you have to keep track of. But make sure you can do interpretations like that. That's going to be important for recitation homework, everything. I mean, that's super important, is interpreting these partial derivatives in a context. All right, any questions on that? Did you follow? Practice. So when you're studying together, just practice saying it to each other and getting all the details right, because that's not easy. Okay. So surface. So we already saw the one surface. So let's look at this one. So this is the function. Well, this is kind of going back to the first one, just finding the partial derivative. So here's a harder partial derivative problem because it involves some more of the rules. So it's not so straightforward. So you want to I'll do attendance, take a minute, see how well you do at finding fx, xy. This is so all you who have been longing for algebra, here's your chance. See how you do on these. So, any questions? Did you agree with what I wrote? People are nodding. So, all the same rules for derivatives still apply. Chain rule, product rule, quotient rule, and then when you're in partial derivative, you just have to force yourself to see that other variable as acting as the same as a constant would. Yeah, Andrew, sure.
On F and Y, is it times that second word?
Everything's times, yep.
Yeah, times, okay.
That was supposed to be a dot.
Okay.
Yep. So that just comes for the ride, and then I was doing times the derivative of that. Are we good? So this is the surface, this crazy surface here. It's also my cape. I had to make it black. So I'll show you, my son loves Batman. I'll show you a nice video on the way out, okay? We got more work to do. All right, so next. We've talked about the algebra, the partial derivatives when they come to the function definitions. And we've talked about what on surfaces. So what else is there here? Do that. We did surfaces. All right, so table. Looks like summer, huh? So this is a what is this? The temperature index, right? Temperature index is how hot it feels at a particular temperature and humidity. Okay, so table of values. So what would partial derivatives look like in terms of a table of values? Okay, so we're going to estimate the partial derivatives of heat index with respect to temperature and with respect to relative humidity at the indicated values. So we'll start with when the temperature is 90 and the relative humidity is 45. So let's get our function notation here. So we'll say the temperature index, I, is a function of temperature, say T, and H. So we're talking about what would the partial of I with respect to t be at 90, 45. So that's the question we're asking first. Partial of I with respect to t, the index with respect to t. So we're going to approach it the same way. So if we're doing the partial derivative of I with respect to t, then what do we do first? Hold h constant. So we're going to look at along here. And we have to figure out, we have to kind of estimate what this multiplier is for that you would multiply your change in temperature by to get the corresponding change in heat index, right? So given a small, we want this number, so that given a small change in temperature, you multiply it by this rate of change and it gives you the corresponding change in heat index. Make sense? So we got to just use what we got. What do we have? What change in temperature do we have? 2. So that's what we got. We got to work with that. We got a change in temperature of 2. And how much does the heat index go up? So we're going to look on either side to get the best estimate. How much does the heat index go up when the temperature goes up by 2? By 2. So 4 here, and so we'll take the average. We'll take about a change of 3.5. So this is about what? Change in index was about 3.5 for a change of 2. Or 1.75. Units on that would be? What's the units on that? Oh, time to go, sorry. That would be degrees Fahrenheit, degrees Fahrenheit that it feels per actual change in degrees Fahrenheit. So that would be your multiplier. Given any change in temperature, to get this corresponding change in heat index, you're going to multiply by 1.75 at this temperature and humidity, 90 and 45. So we'll pick it up there Monday. Here he is.